Hi everybody, it's Mr. Zarze. I bet you've seen one of these before. This is called a Newton's Cradle. One, because we use it to demonstrate physicsy kind of things, and well, rock-a-bye Newton in your physics cradle. Please stop singing and never do that again. Okay, so how does it work? All right. So one ball goes, okay, and the other ball on the other side pops out. What's really going on? Okay, if I take away all but two, look. Okay, one goes and the other one essentially stops. Okay, that's really an example of conservation of both momentum and energy. Okay, and the fact that on this first hit, one stops and the other one goes, okay, that's really a matter of these two things having equal masses. All right, we'll explain that in a little bit. If I take three here, look, ball one hits ball two runs into ball three right away, so we get this transfer of momentum and energy back and forth, and that's conservation. Okay, and so of course we could do this with four. Okay, and then the typical five. All right. So we have to think about it in terms of conservation and transfer of momentum and energy, so it helps see that. Okay, my Newton's Cradle lights up like this. Okay, so we see, look, back and forth, and that's conservation. Okay, if I take two, what's going to happen if I take two? All right, well, I've got double the mass here. So for a given speed, I'm going to have double the momentum. And so if I let it go, two balls go back and forth, and that's conservation. What if I do three? Three balls back and forth, and that's conservation. Okay. If I do four, I don't know if the lights are going to work, but we'll try it. Okay, so that's kind of a hard time with that. That's okay. What if I do two at once? Okay, well, funny thing is I get two independent events, so two collisions. Okay, so two instances of momentum being transferred back and forth, and that's conservation. Okay, I'll try taking one and see. Look, I'll make one go really high and one go a little bit lower, just so you can see that they really do switch. It's not just that they're ricocheting, no, it's two different back and forths, two different examples of collisions conserving momentum and energy. Here, I'll do two and one. See? All right, the law of conservation of momentum and conservation of energy have no regard, okay, for whether or not we're playing with a toy or fundamental particles or a car crash or anything else. It just is. Okay. Let's see. So that was, what was that? It was two and one. Here we can do two and two. Isn't that cool? All right, and then my personal favorite. I guess we could do four and one, but oh well. Let's try that one more time. I need bigger hands. Okay, the lights kind of get a little messed up there. That's okay. I like three and one. And I can actually track the three and the one. Isn't that cool? Back and forth, and that's conservation. Okay. Now, this only works, all right, if we have equal masses. We always get conservation of momentum, okay? We need elastic collisions for conservation of energy, okay? And that's predicated on the bouncing part. See, so if I take a little piece of masking tape, okay, and if I take it and I put it in between, say like two of these balls here, okay, in the middle, okay, just that little tape there, going to cause those to stick together just a little bit. So even though everything's just transferring right through, just that little addition, that little tape, the whole system just completely falls apart. Okay, we still get transfer of momentum. Look at that, they just kind of wind up sticking together, okay, and rocking along. But that effect, okay, where we get the complete transfer of the momentum and energy of one to the next, just goes right away. All right, so one more time, just because it's cool. Here we go. Back and forth, and that's showing conservation. All right? So let's see if we can figure out how all this works. How is it that one ball hits the other balls and stops? Okay, so let's see if we can figure this out using conservation. All right. So rather than trying to think about all five balls, let's just focus on one ball hits the next ball. Okay, when this happens, the red ball would hit the blue ball, okay, and then the red ball stops and the blue ball keeps going. Okay, why does this occur? Well, this is really a special case, okay, so then I have two different balls. All right, I've got this one and this one, just the one and two, okay, but it just so happens that ball one's mass is the same as ball two's mass. So that's the important part. Okay, so starting with conservation of momentum. So we go M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V2 prime. Okay, and kind of the key here is that all the masses are the same. So, we're just going to call these just generic M for mass. Okay, so all of these have the same mass. So there's really no reason to bother with the subscripts. And if that's the case, well, then I can take and factor out all the masses. That's the first thing. All right, the second thing is that ball 2 is initially at rest, so no velocity either. So this really cleans up quite a bit. And we wind up with V1 is equal to V1 prime plus V2 prime. All right, now one solution of this is that V1 prime is 0. If that's the case, then V1 would be equal to V2 prime. So in other words, ball 1's velocity becomes ball 2's velocity, but that doesn't prove anything. That's just one possibility. Okay, the other key to this is that with the Newton's cradle, these collisions are elastic. Okay, and in elastic collisions, we get conservation of kinetic energy. All right, so if we do the exact same kind of trick here, all right, so we have this 1/2 M1 V1 squared plus 1/2 M2 V2 squared is equal to 1/2 M1 V1 prime squared plus 1/2 M2 V2 prime squared. Okay, and just like before, they're all the same mass, so there's really no reason we need to make the distinction between the two masses. We'll just call it generic M. Okay, and then we get to cancel a bunch of stuff. Oh, so satisfying. Okay, we get to cancel out all the 1/2s. We get to cancel out all the masses. Okay, and just like we did with conservation of momentum, ball number 2 is initially at rest. Okay, so all these things go away when this cleans up, so that we get this V1 squared is equal to V1 prime squared plus V2 prime squared. Now, the letters are a little bit different, but this should look kind of familiar. Something squared is equal to the sum of this thing squared plus that thing squared. Something that shows up a lot in physics. I wonder what that is. Okay, I'll let you think about that for the time being. Okay, these are my two equations, and I want to put these two things together, 1 and 2. Okay, I want to combine them. All right, in order to do that, all right, what I'm going to do is I'm going to do a little substitution. Oh, no, I don't want to cut off the E there. Okay, up with equation number 1. See, so I want to work with equation number 1 and shove it into equation number 2. All right, because I don't want to have to worry about any more squareds than I'm already going to have to worry about. Okay, so anyways, I'm going to take and let's leave V1 here, but I'm going to subtract over this V2 prime and set this equal to V1 prime. Okay, that right there, I'm going to take this here and I'm going to substitute that in over there. Okay, so that's the plan anyway. All right, so here we go. V1 squared is equal to V1 prime squared, where I'm going to put in V1 minus V2 prime squared. See, so I'm just subbing in for that V1 prime squared, okay, from my first equation, plus V2 prime squared. Make that a little nicer, V2 prime squared. There we go. Okay, so then I'm going to have to FOIL this out again, or FOIL this out, I should just say. V1 minus V2 prime plus V2 prime squared. Oh boy, algebra. Okay, so then see V first times first, so V1 squared. Okay, minus V2 prime V1. Oh no, I went inner times inner first. Oh well, it doesn't matter. Let's see, so then minus V1 V2 prime. And last times last would be minus V2 prime minus V2 prime. So that becomes plus V2 prime squared. And then there's also this other V2 prime squared over here. Okay, notice that I have this V1 squared and this V1 squared. So I can subtract V1 squared over to the left or over to the right. It doesn't make any difference. These two go away. Okay, and also notice here, look. Okay, negative V2 prime V1 and negative V1 V2 prime. These two things are the same thing. So commutative property. Okay, here I'll rewrite it just so that I can try to make this as clear as possible. Okay, so like, okay, commutative property, look, it's the same thing. Okay, so then I can combine some terms. Okay, 0 is equal to negative 2V1 V2 prime plus, and then I have a V2 prime squared and a V2 prime squared. That's 2V2 prime squared. Let's move over that negative 2 V1, V2 prime, so that it winds up being positive 2, V2 prime squared. Both sides get a 2, so we can divide out a 2 from both sides. And hey, look, there's a V2 prime in there, so we can also factor that out and factor that out. And look at what we're left with here. Okay, V1 is equal to V2 prime. The speed of ball 1 before is equal to the speed of ball 2 after. And if the speed of ball 2 after is equal to the speed of ball 1 before, that's a mouthful. That just says, oh, look, the speed of ball 1 after is V1 minus V1, which is 0. Ball 1 stops after. Ball 2 keeps moving with the speed of ball 1 before, which is exactly what we see in a Newton's cradle. Okay, 1 hits 2, 2 hits 3, 3 hits 4, 4 hits 5. My animation stopped working. Oh no. Come back. There we go. Back and forth. Back and forth. Pretty cool. Thanks for watching.